So I will start my talk by introducing what is In-Stent Restenosis, and will give you an overview of our model. Then I will introduce you our multiscale uncertainty quantification and sensitivity analysis methods. I will report you on the result of the uncertainty analysis of our model, and also I will show you the comparison of uncertainty quantification with different methods, and I will finish with some conclusions. So, In-Stent Restenosis is a re-narrowing of a coronary stent after stenosis was already occurred. And on this picture, you can see that basically stenosis usually is treated by installing a metal stent to the artery. And sometimes it happens that this stent is quite harshly damaged the artery, and the natural healing process becomes too active, and the narrowing process becoming again. And restenosis happens when the diameter of the vessel becomes less than half of the original diameter of the healthy artery. And actually, this happens up to 10% of patients who were treated with, by installing the stent. And we want to use computational simulation to reduce the amount of cases of the repetition of the stenosis. So our model is a multiscale model, and it's very important to mention that it was developed using a multiscale modeling and simulation framework. And the idea is that each of the single-scale model is implemented disjointly, and then coupled through some coupling method. And this we will use later in our uncertainty quantification. So our single-scale components are deployment code which provide initial conditions for our simulation. Then we have a macro model, which is smooth muscle cells. It's another agent-based model which simulates this growth of the cells, growth and split of the cells. And then it sends a geometry to our micro model of blood flow simulation. And this code provides an shear stress of the fluid inside the artery. So we have a challenge that we have two types of uncertainty in this application. We have aleatory uncertainty, which is the natural variability of the macro scale code, since the smooth muscle cells grows randomly. And we have also epistemic uncertainty, which comes from the lack of knowledge on the exact values of our input parameters. And we have deployment depth in the initial condition code, recovery time in smooth muscle cell code, and blood flow velocity in the microscale code. And our goal in this work is estimate uncertainty in our quantity of interest, which is cross-sectional area of the artery. So the methods we are going to first we use is a black box Monte Carlo method. Is the simplest and the most generic method. And to give briefly your idea, if you're not familiar with the method, is that so we have the uncertainty given by some probability density functions in our parameters. We start to sample a value for each of our input. We run our multiscale model as a black box and receive our output of interest. We repeat the procedure of running simulation with different inputs n times, and then using n samples, we are able to approximate the probability density function, mean, and variance of our quantity of interest. But the point is that usually these multiscale simulations are very expensive, and in our applications, we usually have that the microcode takes the most of computational demand, and therefore we want to reduce the computational cost of UQ, because if we will need to run many times our simulations, it can be just it can be just not available this computational time for us. And in this work, we applied multiscale metamodeling, semi-intrusive method, where the idea is that the most expensive computational part of the simulation is substituted by a surrogate. And this surrogate should approximate well the output of this micro model, but produce this result much faster. Usually, metamodels methods for UQ are used to substitute the wall model. And why we have the advantage in this case? In this case, we only approximate one of the input to the macro model, which will produce our final output. And in this case, we expect that the error produced by our surrogate will be less than even if we would substitute the wall model. And then the rest of the workflow is the same as in the Monte Carlo method. Just several details on our surrogate of our blood flow velocity model. So the input to this single scale model is the geometry provided from the smooth muscle cell model, and the output is shear stress provided in the area where the blood is flowing. And this is in our current situation, this is a 2D field, 150 by 150 values. And in this, when we run a surrogate, actually it's become very expensive, and the input and output is of such a large dimension. So our first step was just to reduce the dimension. So geometry, the upper and lower geometry was presented as a vector of the size 150. So we just provided the thickness of the artery, and the output was also became a vector, because actually what is needed for smooth muscle cell macro scale model is the wall shear stress. So we don't need the stress, the wall field of stress. We need only the values on the boundary. So this was our first step to reduce the dimensionality, and I will show you in the results section the result from different surrogate models we applied. First step of Metamodels we produced is simplifying the physical expression, and we assume the Poisson flow, and in this code run much faster than lattice-Boltzmann code, which is in original blood flow velocity of the ISR model. And two other types were data-driven metamodels. One is based on the very simple interpolation, and the second one is a Gaussian process regression. Here there are some details of how we construct, and I think I will not go through the details, but if you are interested in this problem, I will be happy to discuss with you after the talk. And I will then compare the uncertainty quantification results by all these surrogates models. It's important also for me to mention sensitivity analysis. If you're familiar with the study, we use Sobel sensitivity analysis, and it's really recommended method as soon as you measure for uncertainties variance. And what is also important is that with this method we were able to distinguish between aleatoric and epistemic uncertainty. This is very important because aleatoric uncertainty is a reducible type of uncertainty. This is natural variability of your system, and this means that it will stay here. But indeed, we would like to reduce the uncertainty in our response, and this will go to epistemic uncertainty. So to understand which amount of uncertainty came from this epistemic uncertainty is very important, and this was done by, again, using Sobel sensitivity analysis. What is important is that Sobel sensitivity analysis provides a portion of variance. And it's not exactly the same, which is portion of standard deviation, which has the same unit as mean value and would give us more insight on our uncertainty. So we applied Jensen inequality, and when I will report you on the results, I will speak about upper bound of our aleatoric uncertainty and not exact value. So first, our result of uncertainty quantification of response of ISR model. So the first plot is shown the cross-sectional area, solid line is the mean value, and x-axis is time. The blue area is the aleatoric uncertainty, and the red area is the total uncertainty. Second plot shows the relative uncertainty, namely the standard deviation divided by mean value. So what we observe here is that during almost all simulation, we have from 20 to 30% uncertainty, and approximately half of it come from aleatoric uncertainty. So another half is possible to reduce by making more precise measurements. What we also made is we plot the probability density function as the last time step, and what we saw is that the stenosis cases arise around 10% of the cases, which is very close to the physical measurements. And this plot shows the sensitivity analysis, and it's what we expected. So deployment depth at the beginning is a very important value, but indeed because it's in the code which provides us initial conditions, and then the importance of these parameters with time of the simulation drops. On contrary, recovery time become more and more important because this directly affects how long the growth will happen inside the simulations. And the blood flow velocity value was almost equal to the natural variability of the system, which means that it has very low importance, and it can also give us some insight that probably the blood flow velocity or blood flow single-scale model result may not so much affect the final response. Therefore, we can by substituting the single-scale model by a surrogate can be actually a very efficient method, and we should not expect a large error. But let's see what the results actually were. So basically, we are trying to reproduce this free quasi-Monte Carlo result by our semi-intrusive method. And what we see is, so red line, quasi-Monte Carlo result, violet line, and this violet probability density function is the physical metamodel results. And in this model, all the time we overestimate low shear stress. This means the growth is really small, and this is what we see exactly here. Mean growth is very small, and also we obtain a shift to the left of our probability density function, and here it's not visible, but it's around 2% of stenosis cases, which is very low compared to 10% of what we expected. Our nearest point interpolations are these two results. There were two different configurations of this nearest point interpolation, and basically we see that the difference between them is very small, and we receive quite nice approximation. But the stenosis cases result in only 5% in both of these interpolation cases. And the very last result is this one. It is Gaussian process interpolation applied to blood flow velocity. And actually, it was the best result in terms of the probability density function. It gave us around 9% stenosis cases. And we see that the mean value was also very well approximated, and aleatoric uncertainty and total uncertainty was not so good, and almost because of a large spread, it was like a physical metamodel. So, but indeed, our goal was to reduce the computational time of uncertainty quantification, and so one sample of quasi-Monte Carlo of our ISR model takes around 90 minutes. So with, I said we have two different interpolation, nearest point interpolation surrogates. One was a bit more precise, but it was much more expensive. So with the second one, we receive almost 6x reduction in computational time. With our Gaussian process, which was the best, it was, again, almost 6x, but it was more precise that this surrogate. So actually, this was our winner, and we are now actually working a lot on Gaussian process and try to improve them even more. And our physical metamodel, which was not so precise, but it was also almost 7x faster than quasi-Monte Carlo results. So I told you that Gaussian process shows us the best results. So we tried with this meta model also reproduce sensitivity analysis results. And what we saw that the partial variances actually are overestimated, and we explained this because how it is computed, you find the difference between when you change the value of single parameter. And addition to this, we receive also the difference coming because of the error. And so this is why we obtain this overestimation of the partial variances. But when we were estimating the sensitivity indices, we were normalizing these values by the total variance, and it's kind of normalized. And in the end, these measures of sensitivity indices were very nicely approximated with our method. So in this work, we estimated uncertainty of the response of In-Stent Restenosis model. It was very important to see for us that it corresponds to the literature results of the physical measurements. We also show that the semi-intrusive approaches for uncertainty quantification shows us a good approximation of both uncertainty and sensitivity measures, and also give us very good reduction in computational time. And our main conclusion is that there's such a design of multi-scale model when you are able to consider single-scale models as a single black box is very important and can give you advantages when you want to perform analysis of uncertainty. That's it. Thank you very much.